So hello, welcome to the training called Wireshark and Network Analysis. This training will consist of two parts, as was mentioned. My part will be theoretical about fundamentals of TCP IP and networks, and then we will have more practical session about how to use Wireshark to troubleshoot everyday issues. So, TCP IP, I called it the plumbing of the internet because that's quite apt description, and you will see why. Let's begin with 7 layers of OSI. Some of you probably already know what that is, but just for a quick recap, every network infrastructure basically consists of these 7 layers. There are, you could say, generic layers, first 4 ones, and then upper ones, 3 ones are very application specific and application dependent. We will not be touching those high level layers today, and of those low level layers, basically layer 3 and 4 is most important for us because that's where most of the troubleshooting happens, at least as long as it happens on the network level. So, layer 1 is physical, which is basically electricity, optical cables. There aren't really any packets there. The only logical concept there is bits, so basically impulses of electricity, lights, radio waves, etc. And about devices, what would be characteristic? There are such devices called hubs, which are purely electrical. They're kind of similar to switches, but they don't have any logic, basically like electric cords. What you put in one port will be just rebroadcasted on all other ports. So I doubt you ever run into these anymore, but just to illustrate an example of layer 1. And if you want some curse words on this layer, that would be DSL, Ethernet, Bluetooth, Wi-Fi, etc. Basically all the low-level protocols, the lowest level. Then moving on to layer 2, which is data link layer. It's called like that because in layer 2, those bits from layer 1 are assembled into frames. And we have data link here. And most characteristic association with layer 2 would be MAC address. You don't have IP address yet, but you do have MAC addresses. And on layer 2, most common devices are just switches, layer 2 switches. There are switches that also know about layer 3, but most of them are just layer 2. So no routing, no firewalls, nothing, just flat network, and addressing happens only using MAC addresses. Layer 3 is where all the magic starts to happen. On layer 3 we have IP addresses, which are bound to MAC addresses on layer 2. And concepts such as routing, network segmentation are introduced. And well, curse words on this layer would be IPv4, IPv6, and I don't know, IPsec, ICMP, basically those kinds of protocols reside on layer 3. And most characteristic devices are, of course, routers. So, and on layer 4 we have transport layer, and here TCP and UDP are introduced on this layer because they are called transport layer protocols. And well, there's not much to say about this layer, at least I do not have much to say, but this layer does some additional data integrity checking and correction. Some of that already happens on layers 2 and 3, and the layer 4 is a bit more sophisticated. But all you really need to know is that TCP and UDP are on layer 4. I will not touch really layers 5, 6 and 7 that much because they are very specific, but just to illustrate, layer 5 would contain such protocols as NFS, SQL, RPC and similar. Layer 6 is presentation layer, and presentation means that data is presented in some format already. So here you would have encryption, JPEG, MIDI, basically any kind of data representation that becomes is already a bit readable to humans and to applications. And layer 7 application layer is the very last layer in this structure. And well, most characteristic description would be you have HTTP on layer 7. HTTP is purely layer 7 protocol, as is Telnet or SNMP. And this is very, very application specific, so not much else I can say here. And now the most important part on layer 4 is TCP versus UDP and how these two are different. So in short, TCP is, well, the name says itself that it's transmission control protocol. It's very concerned with controlling transmission, with controlling integrity of data, avoiding corruption, and things like that, while UDP is quite the opposite. And TCP is very reliable, but it's also very slow because it has big overhead, since it does all these checks and retransmissions and acknowledgements. It is also stateful, which means to communicate over TCP you need to establish a session and you need to keep track of the state of the session, and that also makes it a bit slower than UDP. While UDP is very fast because it doesn't have that much overhead, it is lossy, it can lose some packets, and it will not be a big deal if you implement it correctly. It doesn't have any connections, it doesn't track connection states, it doesn't have acknowledgements, and that's why it's so fast. Also, as I said, TCP does flow control, while UDP does not do any flow control. And TCP does both error checking and error recovery. UDP does error checking, but it cannot recover. It means you are able to detect errors and drop those erroneous packets, but you will not be able to recover as well as with TCP. And one more thing to mention, that TCP tracks packet order. On UDP you don't have that, and the application itself has to do tracking of packet order. One very important aspect of UDP is that it has broadcast support, and why is that important is that that's the only way you can do DHCP. You cannot do DHCP on TCP because TCP doesn't have broadcast support, and if you know what DHCP does, it's really not possible to do it any other way. Also, UDP is very often used for cases such as DNS, where you have a very uneven communication, uneven in a way that there's a lot of small requests from client and few requests from servers. So very often DNS is done using UDP to avoid overloading servers, because there are a lot of small requests coming in, and the DNS server doesn't have to keep track of the state of each and every request. It just receives requests and responds to the clients over UDP and conserves resources. So basically UDP just spits out packets in high speed into your direction, and it doesn't really care. Did you receive it? You didn't receive it? It doesn't matter. So that's why it's often used for video broadcasts, for VoIP, because if you lost one packet on video broadcast, worst that can happen, you will lose one frame, no one will even notice. Same with voice and with some games. But if you lose one packet in executable, it could be that executable will be unusable, and even worse if you lose one packet in database transaction, so entire transaction could be corrupt. So that's the case of TCP versus UDP. Okay, now we'll go to TCP in more detail. And the first thing that you need to know when dealing with TCP is a three-way handshake, and this is known as SYN, SYNAC, ACK. And why it's so important? Because all the negotiation about the connection will happen on this handshake, and entire connection quality will depend mostly on what's decided in this handshake. So as you can see in this scheme, client first sends SYN packet, which is basically a hi to the server, and then the server sends back SYNACK packet, which is basically saying, yes, hi, I can hear you. And the last packet in this three-way handshake is client again sends, okay, that's great, I can see you hear me, so let's start talking now. And here data transfer starts. Now, about this handshake, one note that I like to mention is a vulnerability security issue with this handshake because of attack called SYN flood. It happens when a malicious client starts sending a lot of SYN packets, just flooding the server with SYN, and it doesn't care if server responds or not. The attack works that way that server must keep state of each SYN packet in its memory because it considers every SYN packet a beginning of new connection. So by flooding server with SYN packets, you can effectively exhaust its memory, causing denial of service. So that's quite a weakness of this handshake. This is an example of how this handshake looks in Wireshark trace. You can see those three packets going back and forth, and you can also see important parameters decided in there, which we will discuss right now. And after connection initiation, another important thing to know about is connection termination. Most common way, most often used, is very similar to three-way handshake. It's the sequence of FINAC, then timeout, and then closing the connection. Another alternative and faster way is to send reset packet, which closes connection immediately without timeouts. And the important difference is that first way is not very light on resources, which means that server again must keep track of connection termination state, wait for predetermined time before finishing the connection, and it consumes memory, while RST packet basically terminates connection immediately and frees the resources. And RST packets by default in Wireshark are colored in kind of red color, which you might think indicates a problem. It sometimes does, but not always. In some cases, actually, a reset is the best way to terminate the connection to preserve resources, especially in cases where you have a huge number of short-lived connections. So in traditional way, you would need to do this long FINAC, timeout, close for each and every connection. And that's a problem because it can exhaust memory. The proper way would be to send reset packets to end connections, which terminates them immediately and frees up memory and resources. So this is the example of regular connection termination, that three packet sequence in the Wireshark, and this is how it looks on the computer or on the server. Basically all those connections that you terminated, they are still in the memory, they are using resources because they are, server must wait for predetermined time before finishing the connection. And if you have like a huge number of connections that are short-lived, it can exhaust your resources quickly. This is the way to terminate connection using reset packets. You can see several connection terminations here, and by default they are in color red. But as I said, it depends if this is a problem or if this is just an efficient way to terminate connection. So in every case you need to investigate. Now, one feature of TCP is MTU, which is maximum transmit unit. It actually exists also on layer 2 and layer 3, and it is just a size of a frame or packet that can be transmitted across the network without fragmentation. So frame would be on layer 2 and packet would be on layer 3. Most typical sizes are on layer 2 you have 1518 bytes, and on layer 3 you have 1500 bytes, because those 18 bytes is layer 2 header, which need to be subtracted when going to layer 3. Now, important thing to mention when talking about MTU is that any kind of tunneling or encapsulation will again reduce the MTU of actual data protocol. And every time you have tunneling or any kind of similar encapsulation, it happens this way, that there's a passenger protocol which carries your data, and there's a transport protocol such as general routing, encapsulation, etc. And your passenger protocol's MTU is reduced even further, so data transfer will be slower. Now on layer 4 we have MSS, which is maximum segment size. And it's not the same as MTU, because MSS tells exactly the amount of data in a single TCP packet, excluding TCP header. And originally it was limited to 64 kilobytes, but we now have extensions to allow us to use much larger MSSs, otherwise we would be unable to have fast networks. And MSS is basically just MTU minus 40 bytes. And those 40 bytes consist of 20 bytes of IP header and 20 bytes of TCP header. So, hence, most typical size is 1460 bytes. And this is where you can see MSS advertised in Wireshark trace. It happens in the handshake process. So once again, this is why it's so important to always capture a handshake process when troubleshooting. Because if you do the capture and you miss the handshake process in the capture, you lose a lot of information about the connection. You're kind of in the dark on certain aspects. Now, another important thing to know about is receive window size. And receive window size is basically telling you how much data can be buffered in the receiver's TCP stack per this particular connection. So basically, when sender sends data to the receiver, it keeps track of that window size. And if it sees that receiver's window is full, it stops sending data, and vice versa. The receiver can send a packet saying, oh wait, my TCP window is full, I cannot receive any more data. And then connection stalls and nothing is sent. And why that happens usually is that the application doesn't pick up the data from the TCP stack buffer. So that's the most common reason. That could mean that either server is overloaded and the application just isn't fast enough to pick up data, or application itself is malfunctioning, and that's why that data is kept in the TCP buffer for a long time, and buffer fills up and connection isn't broken, but it also doesn't send any data, and you get very slow transfers, you get delays. So you need to watch this in traces too. So now this is an example of case where everything is fine and receive window size is not reduced, which means application is performing fast, server is fast, and all is good, and not once so it happens that TCP receive window size would be reduced through entire connection. And this is an example where there's a problem with the server, with the application. As you can see, with each transaction, receive window size is reduced, which means data is being accumulated in TCP buffer. One important thing to mention that big receive window sizes are necessary if you want to take advantage of fast networks, especially of fast networks with very high throughput but also very high latency, so fast WAN links. Because if receive window size is not big enough, it will be mathematically impossible to reach full potential of the link. There are even calculators for that. My colleague in the second part will show you one of those examples where you can enter link latency and enter your receive window size, and it will calculate the maximum possible transfer speed that you can achieve. So even if you have like 10 gigabit link with a latency of 10 milliseconds, but your receive window size is small, you will never reach that 10 gigabit speed. There's no way. So always watch this when looking in the traces. If you have slow transfers, you cannot figure out what's happening, check the window size. Small receive window size will prevent you from reaching high throughput. And this is an example how it looks in Wireshark trace when the receive window size is filled up, when the receiver's TCP buffer is full. So connection is alive, but nothing is sent over that connection because the chatter goes back and forth. My window is full, I cannot receive data, wait. So that's an issue, and most often means that application didn't pick up data that was sent over the network. And the receive window size issues are most commonly observed on applications that just move huge amounts of data, and that's most characteristic for backups, for large file transfers, and basically any kind of very large data transfers over the network. If there's a performance issue in such cases, definitely try to look for receive window size problems. So one of the extensions that was introduced on top of original TCP IP stack is window scaling. As I mentioned, originally TCP had a maximum possible receive window size of 64 kilobytes, which is not enough these days with our networks. Thus, we now have an option called window scaling. It's basically a scaling factor or just multiplier for receive window. So in traces you usually see receive window size and then window scaling factor. You multiply those values and you get the actual window size that you will be using for the connection. And important to note is that even if you are not using window scaling for a particular connection because there's no need for that, there should be indication that you do support it. So in the handshake, even if window scaling factor is not used, there should be indication that it is supported, because if there's no indication of window scaling support, it usually indicates maybe not an issue, but it's typical for very, very old systems, old TCP IP stacks. So most of the time there should be support for window scaling, even if window scaling is not in use. This is an example how you would see window scaling in Wireshark trace. As you can see, you have a window size value and then window scaling factor. Multiply those and you get actual receive window size. This is from actual trace, so it's for that connection it was normal window size of 255.168 bytes. And again, window scaling multiplier will be sent only in the initial packet of the handshake. So again, you have to have initial handshake of the connection to know what window scaling factor is used. So again, every time you're troubleshooting, make sure to capture initial handshake. And that window scaling factor cannot be changed for the connection. You have to break the connection and initiate new one to change it. Another important thing that is much less talked about is don't fragment bit. What it does is, as I mentioned, there's a thing called MTU, maximum transfer unit, and those things exist both on layer 2 and layer 3. And if you attempt to send packet bigger than MTU of, I don't know, third router from you, that packet can either be fragmented into smaller packets and sent further, or if it has don't fragment bit, you will then receive the response from the router, special ICMP packet that says fragmentation needed, but no fragment bit set. And that is good, because this way your software knows that somewhere along the path of the network, MTU was too small for your packet to fit, so you decrease the MTU and send a smaller packet. And this way, PMTUD or path MTU discovery happens. So if firewall admins would block all kinds of ICMP traffic, which they sometimes do, and not implementing any alternative way of discovering MTU or fixing MTU, the network will be effectively broken and you have intermittent issues and it will be very bad. So there are alternatives to this. In our infrastructure, I was told that we are blocking all kinds of ICMP traffic, but instead we are implementing MSS adjust, which is another way to deal with MTU and big packets. So don't fragment bit is also observed in like 99% of all packets, and it should be there. Because if there's no don't fragment bit, it means you are allowing network gear to split your packets, to fragment your packets and send them fragmented. And fragmentation, well, it's in itself might not be bad, but well, it's undesirable, because you can have various kinds of problems with packet fragmentation, and should avoid it and use either PMTUD or other means to deal with MTU and packet sizes. Another very, very important, and one of the most important for performance extension introduced in TCP/IP stack is selective acknowledgements. Because initially, basically every single packet had to be acknowledged by the receiver. So I send you one packet, you say, I got it. I send another, you said, I got it, and like for each and every packet. And that's very big overhead, and right now we have quite reliable networks, quite fast networks, and this overhead is really unnecessary. So SAC, or selective acknowledgement, was introduced so that receiver can acknowledge packets in batches. You don't have to acknowledge every single packet. You can just selectively acknowledge big batches of packets, and then if some packets are lost, the sender will retransmit only those few lost packets. Without this, what would happen if you send a huge chunk of packets, and then in that chunk some middle packet was lost? You would have to retransmit not just lost packet, but everything that came after that, which is very ineffective. So this selective acknowledgement allows us to avoid this and optimize data flow. And again, it has to be supported in every modern system. You should expect it to be there. If you don't see selective acknowledgement support, that means you need to investigate. It's not good. It should be supported. And this is how you can check if selective acknowledgements are supported. So again, in the handshake you will see this option SAC perm equals 1, and it has to be there. If it's not there, you should investigate. Last thing I want to mention from my theoretical part is a thing called TCP segmentation offload. And why I want to mention it, because I was talking about MTUs and packet sizes, but there can be cases where you will see in the traces packets being sent that are much bigger than MTU. And usually what that is because your network card has CPU for various kind of things, and one of those things is automatic segmentation of TCP packets. So basically it takes the load of the operating system and handles inside the network card. An operating system can just send large packets, not caring about MTU and fragmenting them, because segmentation offload will allow network card to deal with this. And in such cases you will see in network traces packets bigger than MTU. So don't be surprised, it's probably TCP segmentation offload in action if you see things like that. Also in some drivers it's called large send offload, and it tends to cause issues in some cases. So when troubleshooting, one of the things you might consider in certain cases, turning off large send offload or TCP segmentation offload in network card driver options, which sometimes solves the issue, but just a thing to keep in mind. And that's the end of my part. I guess we will have a short break now and then practical session with Marius. Unless you have some questions for me from this part. Okay then. Thanks for your attention.
Thank you.